All right. So today and the next couple days, I want to talk about thermodynamics, which seems the least biological of all the things I'm going to talk about. But it's actually extremely important for understanding how biological things work. It's also the kind of place where there are a million pitfalls. My feeling about thermo is if you think about it sort of and stay on the straight and narrow, you get it, you understand it, you're fine. But if you stray off the path, it's really easy to get very confused and think about things the wrong way. And there's lots of traps for the unwary. So I want to make sure I get this business clear today, and that's what the snap bracelets are partly about, is to understand how this business works. So let's take it piece by piece. So the reason we care about this is the major goal of living things is controlling chemical reactions. In fact, you could almost define life as a set of carefully controlled chemical reactions. As an example, I want to digest my lunch to monomers. That is, if you remember from way back when, we talked about you are what you eat. So you have your lunch, a cheese sandwich or whatever. You are not a cheese sandwich, but you contain the same amino acids as a cheese sandwich. You have to break it down to amino acids and then reassemble it into you. The thing is, there are two issues. One of them is that I do not want to digest my lunch all the way down to atoms. I don't want to blow it up into little tiny pieces. I want to make it into useful pieces. That's one task. And that is, so cells want to control which reactions happen. Okay. And number two, I want this to happen sometime soon. That is, I want to have my lunch, I remember my breakfast digested by sort of late morning, my lunch digested by early afternoon, so I got some energy and I'm ready to go, and pieces to make more of me. So the other thing that you care about, not just which reactions happen, but the other question is how fast. Need to control how fast they happen. So controlling which reactions happen and how fast they happen are extremely important for every living thing. Right? You would not be here today if your body couldn't have unbelievably exquisite control over exactly which reactions happen and how fast. So like in the prototypical example is digesting your lunch. You want to digest, you just want to break the peptide bonds. No other bonds. Just break the peptide bonds. And you want to do it quick so that you can get use of lunch sometime today. All right. So what I wanted is to understand that, there's a bunch of things you got to know. There's a bunch of important ideas. And there's one, I'll call it an illustrative example. And that is the SLAP bracelets. Right, or SNAP, depending on how you want to call them. And I want to define one thing. This triangle symbol we'll see a lot. This is read as delta. And it means change in. So delta whatever is a change in it. Delta my bank account is a change in my bank account. All right. Fair enough. What I want to do, you may have seen diagrams like this before, you may not, but I want to take you through one of these. There are two states of this snap bracelet that we're going to care about at first. One of them I'm going to draw out like this, the straight state. And then there's the coily state, the coiled. Right? And you probably all saw them. So this is the straight state, right? And you can transform it reversibly between the coiled state and the straight state. Right? So we want to talk about this from a thermodynamic point of view. So I hope everybody had a chance to snap it and slap it and check it and see what was going on with it. And I want to draw a diagram here. Let me even give myself a little more space. This is going to be from high to low, and this is PE, that is potential energy in the bracelet. Okay? And this is and down the bottom axis here, and this is where one of the many places people goof up. These are different states of the bracelet. So what I want to do is I want to put on this graph, on this chart really, it's not so much of a graph as it is a chart, different states. I'm going to have the coiled one over here and the straight one over on this side. And I want to know their potential energy. Not exactly the difference, but which one's higher? Are they the same potential energy? Is one higher? Is one lower? If they're different, which one's got the high potential energy? And again, to be really clear, the potential energy in the bracelet. Right? So is this the high potential energy state, or is that the high potential energy state? And really importantly, why? So it's one of the things, talk to your neighbor, argue about it, we'll call names. Which is the high potential energy state, straight or curly, and why? While you're thinking about it, hey everybody, I want to throw another word in now that you started talking. That other word is stable. That is, one of these states is more stable than the other. And that might be a useful way to think about which is the high or the low potential energy. So think perhaps about stability and potential energy that way. That might be a useful way to look at it. So which one's more stable and all that. So take a couple more minute or so and talk about it, and we'll get down to business. All right, so get a consensus, stability, potential energy, blah, blah, blah. And let me call a name. Andrew Caruso. Andrew. So, tell me, which one's higher, one's lower, they're the same, what's the deal? So Andrew says when it's straight, it's got higher potential energy. And your argument for that is? It takes less to get it to go to coiled, right? It takes a little tiny flick to get it to coiled, but it takes some serious work, well, sort of serious work, to straighten it out, all right? So it takes more energy to straighten it than to kink it, all right? How does, did you guys talk about stability?
Right, well, it's less stable and less stable.
So what he said is this is a less stable state because it's far more likely that this thing is going to kink up on its own. Like, for example, if I just drop it, sometimes if you just drop it, or if you, well, that was a great demonstration, if you actually just touched it and it flipped, but it's almost never going to happen that you're never going to have it coiled and have it snap to straight. All right? And so that's right. So that was what I was after. So let me put these on the graph. Thank you, Andrew. So what we've got here, the straight state has the high potential energy, and the coily state has the lower potential energy. Right? And there are several different words to talk about this. This is unstable, relatively speaking, and this is stable. What I should really say is more stable, less stable, but that is unstable, it is likely to change. Right? State. And this is unlikely. State. All right? Questions about that before we talk about, there's all sorts of cool stuff that comes from that, but just from there. Maybe she was with me on high potential energy, low potential energy. What's going on with that? Okay. So there's a couple things we can add about the transitions there. And I'm going to use different colors for these. So, actually, let me do the green one first. Green. So, we can talk about two different processes, this away and the reverse. This chain, and there's a couple things we can say about this. This thing, and actually let me draw the reverse reaction too. So, like most chemical, we're going to make an analogy to chemical reactions in a little bit, but like most chemical reactions, this turns out to be reversible. Some are more easily reversible than others, but you can actually go from one state to the other in either direction. So one of the mistakes people oftentimes make with graphs like these, they call them reaction coordinate diagrams, there's lots of different names for these things, is they think that this is a time axis. So you always go this way, right? You go from long ago to now, or now into the future. The time moves this way. That's wrong. That's not, it's really important. This is more like a map than it is like a graph. It says that's lower energy and that's higher energy. So if I go this way, I'm going up in energy. That way, I'm going down. And I can go either way. Right? So it's not a time axis, which is really one of the important things to keep straight. All right. So let me say some things about what those lines mean. This reaction releases energy. That is the snap. You know that, right? If you whack it, you can actually get spanked by it if you do it wrong. It can actually hurt you. There's energy released. And you're turning the potential energy into kinetic energy, if you like. This is also would be called the favored reaction. It is more likely to happen. It is also spontaneous in a thermodynamic sense. And the energy of the bracelet decreases. So that means that the delta PE is negative. Right? So the potential energy, let me write that E really nice and neat, is negative. Right? So that is high potential energy, low potential energy. From the point of view of the bracelet, it has less potential energy. Energy is conserved. That energy goes into slapping my hand, making some noise, getting the environment a little bit warmer. But this is high potential energy, and this is lower potential energy. And that energy gets given off as heat or whatever. All right. Likewise, the reverse is true for all. The opposite of those things is true for the reverse reaction. So this thing, you must put energy in. How do you know that, right? Once it's coiled, it takes some work. You got to stretch it out, right? Well, I'm exaggerating, but okay, you got to stretch it out, right? So you got to put some energy in. Likewise, this is the unfavored reaction. It is non-spontaneous. Okay. And here the energy of the bracelet increases. So delta PE is positive as you can go in that direction. Make sure I got all the pieces of that. So we're going to draw free energy diagrams like this of molecules, and that's what it's all about. It's the energy of the molecule. So when you talked about the TNT molecules, TNT is unstable. It's high energy, and the products of TNT exploding are down here, lower energy. And the difference in energy is given off as kaboom, right? The sound and heat and light and all of that comes out. Okay? So the products of the explosion are stable, TNT is unstable. So it's the same sort of thing as this. Right? Questions about that before we talk about it? There's a very important detail I have left out.